Sine, cosine and tan can be deceptively tricky, and the principal reason for this is that each function takes the same value at a potentially infinite number of different angles. For example, the sine of some unknown angle theta is equal to 0.5. Well, if you always had the appropriate graph to hand, it would be easy. And I can see here when sine takes the value of 0.5, the angle is 30 degrees, 150 degrees, 390 degrees, and 510 degrees. And in fact, I can go the other way as well, and I can see the angle is also minus 210 degrees. And if I extended the graph, I could find yet more solutions. It's for this reason that when dealing with trigonometric functions, we specify an interval, otherwise we could just go on forever. But the truth is, usually you don't have a graph to hand. You've just got your calculator, and I can use my calculator to find theta equals 30 degrees. The problem is my calculator gives me only one of the potential solutions, and it will tell you one of the solutions is theta equals 30 degrees. So what am I to do? Well, I could draw a quick sketch of the curve. And using my knowledge of the sine function, its important angles, its symmetries, and its cyclical nature, I can work out the other angles. Because of the symmetry, I can see that if I've moved 30 degrees from here, I also move 30 degrees from here to reach the same position, and so here we have 150 degrees. And I also know that the function repeats every 360 degrees. So if 30 degrees is a solution, so is 390 degrees. And similarly, if 150 degrees is a solution, so is 510 degrees. I can go the other way too and subtract 360 from each of these solutions. And if 150 degrees is a solution, so is minus 210. And if 30 degrees is a solution, so is minus 330 degrees. I'll just say now that being able to find additional solutions in this way, as a result of having a good working knowledge of the graphs of sine, cos and tan, is crucial. And only once you can do this, should you then move on to the cast method, which this video is about. You should really view the cast method as a time-saving device and definitely not use it to avoid having a full understanding of the trigonometric functions. Such a gap in your knowledge will cause you problems later on. So here we come to the cast method. And the first thing you need to be able to do is draw the cast diagram. And this is what it looks like. It's very important that you understand a few things about the diagram, otherwise it will always seem a bit confusing and probably a bit hit and miss. Firstly, you need to know how to draw in the angle you're evaluating. And we always start here, the positive x-axis, and positive angles rotate in a counterclockwise direction, whereas negative angles rotate in a clockwise direction. For example, an angle of positive 30 degrees would be drawn in approximately here. An angle of positive 250 degrees will be drawn in approximately here. And an angle of minus 200 degrees will be drawn in approximately here. And we could even draw in an angle of 460 degrees here. I'll also add this is how you read angles from your completed cast diagram. So for example, this angle would be read as 150 degrees, since we always start from this reference position on the positive x-axis. We could continue rotating through 360 degrees, and so this could also be described as 510 degrees. And if we choose to move in a clockwise direction, giving a negative angle, we could also describe this as minus 210 degrees, and indeed we could carry on rotating around in just the same way. This shouldn't surprise you if you understand the cyclical nature of trigonometric functions. I'll just draw your attention to this angle here, which we call the related acute angle, and they are always measured from the nearest x-axis, no matter which quadrant your arm is in. As a result, they will, as the name suggests, always be acute. And to keep things simple, I suggest that these are the only angles that you should actually write in on your cast diagram. For example, if I was interested in an angle of 280 degrees, I would draw the arm in here, and the related acute angle would be 80 degrees, since it's drawn from this nearest x-axis. The second thing you need to understand about the cast diagram is that it shows you for any given angle whether the sine, cos or tan function is going to be positive or negative. And to that end, these letters show which trigonometric ratio are positive in each quadrant. So for example, any angle drawn in this quadrant will be positive if it were sine, and conversely negative if it were cosine or tan. What about an angle that would fall in this quadrant? Well, you should be able to see that if it was a cosine function, it would be positive, but a sine or tan function in this quadrant would be negative. A stands for all, and any angle that falls in this quadrant will result in a positive trigonometric function, whether it be sine, cosine or tan. So now I've explained the important background information, let's use the cast method to find all solutions to sine theta equals 0.5. We use our calculator to find an answer. Theta equals 30 degrees, but this is only one potential solution. Step 1, we draw in the arm of our angle, in this case 30 degrees. Step 2, write in the related acute angle. Step 3, identify the sign, positive or negative, of your function. So we have sine, and we know sine in this quadrant would be positive because all functions are positive. We find the matching quadrant where sine is also positive, and that's here. And we draw in a second related acute angle of 30 degrees in this matching quadrant. Step 4, we read off the angles. Remember, we always start from this positive x-axis. So we have 30 degrees, 150 degrees, and we can cycle all the way around through 360 to give us 390 and 510 degrees. But don't forget, we can also move in a clockwise direction to give us negative angles. Minus 210 degrees and minus 330 degrees. And you can keep cycling around to build as many solutions as you need, depending upon the interval demanded by the equation. Here's another. Cos theta equals minus 0.4. So we'll use our calculator to find at least one potential solution. And in this case, theta equals 114 degrees to the nearest degree. Just as before, we draw in the arm of our angle, 114 degrees. We write in our related acute angle from the nearest x-axis. We identify the sign of the function in this quadrant. Now, it's cos that we're dealing with, and this cast diagram tells us it's only sine that's positive in this quadrant. So we know our cos function is negative. Now we need to find the matching quadrant where cos is also negative, and that's this quadrant here. Since cos would be positive here and positive here. And we draw in a second related acute angle in this matching quadrant. Remembering it's always measured from the nearest x-axis. And finally, we read off the angles. So we have 114 degrees, and if we carry on moving around, 246 degrees. And in fact, if we want, we can cycle through 360 degrees to give us 476 degrees. Similarly, we can move in a clockwise direction for the negative angles, and here we would have, for example, minus 114 degrees. And you can cycle round as many times as necessary to build as many solutions as required by the interval given in the equation. We'll do one more. Here we have tan theta equals root 3. We'll use our calculator to give us at least one potential solution, theta equals 60 degrees. And then we'll use our method as before. So we'll draw in the arm of our angle, 60 degrees. I'll write in my related acute angle. Tan is positive in this quadrant. The other quadrant where tan is positive is here. And so I'll write in a second related acute angle in this matching quadrant. Finally, I'll read off the angles. If I move in a counterclockwise direction, I'll get positive angles, 60 degrees, 240 degrees, and I can cycle through 360 to give me 420 degrees, and so on. Again, if I want negative values, I'll move in a clockwise direction. Can get minus 120 degrees, and if I continue to cycle round, minus 300 degrees. And you can cycle through minus 360 again if you need more solutions depending upon the interval of the equation, which I've not given in any of these examples. And there we have it.